Hello, so my name is Persigali Malfamo.
Okay, guys, so Team Klein, Godfred.
Hello guys, so my name is Desmond Abisi Selassie.
Hello guys, my name is Alan Nkrumah.
Okay guys, so I go by the name Stephen John Bempon.
Yeah.
We are Abdul and we are presenting on the memory systems.
Memory addressing.
The flip-flop as a single-bit storage cell.
The D flip-flop.
And I'll be giving a summary on everything that we present.
So then we ask the question, what's the computer memory system? The computer memory system is also known as the memory hierarchy. It refers to how the computer system stores and retrieves data in the computer. The memory system consists of different components ranging from the cache memory, the register, all the way down to the secondary storage. All these levels are needed by the computer for balance, speed, and capacity in the computer system. So we'll move on to the memory hierarchy. This is a diagram to describe the various components of the memory system. The first is the register from the diagram, followed by the cache memory, the main memory, and the secondary memory or the secondary storage. The higher the component is from the bottom of the diagram, the faster and less denser it is. This simply means that the higher the component is from the base of the diagram, the faster it is, hence able to read and write data faster than any other one. And the less denser it is, hence the storage capacity is low. The first of the computer hierarchy I would like us to consider is the register. The computer register is a very small and fast memory that is built into the CPU. It holds data for the CPU for processing. How does the register work? There are buffers that stores data copied from the main memory so that the processor can fetch the data whenever it needs it. So the register works by storing data and instructions that the CPU needs to access quickly during processing. This process by the register helps to improve the speed and efficiency of data manipulation in the computer system. We will then move on to the cache memory. The cache memory is a special storage space for temporary files that makes device browser or apps run faster and more efficient. The cache systems allows you to efficiently reuse previous retrieved data. The efficiency of the cache can be measured using the hit ratio. So the hit ratio is simply described as the measure of the cache's efficiency. And to be able to calculate for the hit ratio is given as the number of hits divided by the total number of the main memory. Although the memory needs data to be able to perform its function, there may be at times where it may be lacking this information. Hence, it won't be able to provide the needed data to the CPU. So to be able to calculate this miss, we use the miss ratio. It's called, or is explained as the portion of memory reference not satisfied by the cache. And it's also given as 1 minus the hit ratio, which is the number of hits divided by the total number of the main memory. So the cache memory is divided into three different parts. We have the level 1 cache. This is the primary cache and is usually embedded into the processor chip as a CPU cache. And the level 2 cache, which is the secondary cache, it is also sometimes embedded on the chip or on a separate chip. The level 2 cache has a high speed alternatively system than the level 1 cache. The level 3 cache is specialized memory developed for improving the performance of the level 1 and level 2 cache system. Yes, so we'll move on to the main memory. So the main memory is also known as the RAM. The main memory is the primary storage device or primary storage medium used by the CPU to hold data and instructions temporarily. So what makes the main memory different from the other memory components in this system? The RAM is easily read and written to by the microprocessor, and it is able to access any address at any time. The RAM is the most volatile of all other components in the memory system. So the RAM being the most volatile simply means it loses its data right after there's a power cut, or it loses the supply of power. The main memory is faster than the secondary memory because of the way it stores and retrieves data. Hence, it's a volatile memory. Volatile memory uses electronic circuits to store data temporarily. This makes it easy to access because it does not require moving parts or mechanical processes, unlike the secondary storage. There are different types of main memory. We have the dynamic RAM, the static RAM, the synchronized dynamic RAM, the double data rate synchronized dynamic RAM, and many, many more. Yes, so we'll move on to the secondary storage device. The secondary storage, they are non-volatile storage system, unlike the main memory, which is a volatile. And they are able to store memory or data in a long term. So what is the technology that the secondary storages use, which is different from the various or the other components of the memory system? They are able to maintain data even when there is a power cut. They do this by the use of technologies like the magnetic disk or flash memory. So this process makes the secondary storage a very slower storage. Why? The secondary storage is slow because it involves mechanical processes, which is also the moving parts of the secondary storage to be able to access data, or complex electronic operations to read and write data. Hence, this process consumes time before the actual data is being read or is being written onto the storage media. There are different types of secondary storage media, ranging from the hard disk drive, solid state drive, the USB flash drive, and then the cloud storage. Because of time, we'll consider only the difference or the trade-off between the hard disk drive and then the solid state drive. The first is the speed. Comparing the speed between the hard disk drive and the solid state drive is faster than the hard disk drive. And then the capacity. The hard disk drive has higher capacity or is more denser than the solid state drive. This simply means it has high storage capacity than the hard disk drive. And we'll talk about the power consumption. The hard disk drive has lower power consumption compared to the solid state drive. The cost of the hard disk drive is lower also than the solid state drive. So these are the different components of the memory system, which are the first one, the register, the cache memory, the main memory, and the secondary memory. So all this memory comes together to provide balance and speed in the computer system. But they all have different speed capacity, which is one major difference between all of them. And the influencer, or what causes the difference between, or what causes the difference in speed, is the nearness of the storage media or the storage component to the CPU. So if we take note of what I mentioned earlier, I said the register is located inside the CPU. So that is one reason why it is the fastest memory system, followed by the cache memory, the main memory, and the secondary memory. And the secondary memory is the slowest because it's nowhere near the CPU compared to the cache memory and the register memory. So these are the different components of the memory system, which are the first one, the register, the cache memory, the main memory, and the secondary memory. So all this memory comes together to provide balance and speed in the computer system.
Hello. Welcome to today's lesson. Okay, so our lesson will be on memory addressing. Okay, so let's get straightforward into the lesson. For today's lesson, we will be looking at the introduction to memory addressing, the big and the little endian memory organization, the byte ordering, the word-oriented memory organization, and finally, types of memory addresses. So let's begin. First of all, what's an address? So an address refers to what? A byte of memory. So conceptually, memory is a single, large and array of bytes, each with a unique address. So address here can be what? Index. And then each address is just a number of represented in fixed length binary. So programs also refers to bytes in memory by their addresses. Domains of possible addresses is also what? The address space. So we can say that we can store addresses as data to remember where other data is in memory. So address here means what? We want to what? Store addresses of data in a memory. But not all values fit in a single byte. Many operations actually use multi-byte values. Now, this is a trial question that you can pause the video and try later. But let's move on. So, the memory of a computer consists of tiny electronic switches, with each switch in one of two states, that is open or closed. And it is, however, more convenient to think of these two states as zeros and one, rather than open and closed. Thus, each switch can be represented a bit. And the memory unit consists of millions of bits. In order to make memory more manageable, 8 bits are grouped into bytes. So take note. Memory addressing is what? A fundamental concept in computing that refers to the process of what? Storing, retrieving data from a specific location in a memory. So here, memory addressing, all that we want to know is what? We want to know how data is being stored in the memory so that we can be able to what? Retrieve it later in the future. And then memory addresses are used by software and hardware at various levels to reference a specific memory location. So memory can then be viewed as consisting of an ordered sequence of bytes. Each byte in this memory is identified by its sequence number starting with 0. So let's look at this diagram. So this is the logical view of the system memory. And then, this is the logical view of the system memory, and it's being represented in hexadecimal figures. It's being represented in hexadecimals. Yeah. Okay. And this is referred to as what? The memory address of the byte. So such byte addressable because each byte has a unique address. So now let's look at this. The divisions we see in this diagram, what? The divisions we see in this diagram tells us that what? Each division has a unique identity. So we can be able to what? Reference it later when we want to retrieve our data that was being stored. Let's move on. So let's look at machine words. Instructions encoded into machine code, that is zeros and ones, as we saw earlier, as open and closed. And then historically, still true in some assembly languages, all instructions were exactly the size of a word. We have chosen to tie word size to address, that's the word. So a word size is equal to what? Address size, and that is the register size. And then a word size, a word size is equal to what? 2 to the power W. I think we have made this in mathematics or somewhere. You can reference later. And then current 86 systems use 64-bit byte words. That's the potential address space, 2 to the power 64 address. You can type that on your calculator to see the output. So, word-oriented memory organization, so address still specify locations of bytes in memory. So, as you can see here, So as you can see on the screen here, okay. So the address for adjacent word would differ by 1, and the word addressable system, as mentioned earlier, also differ by 4. So it is necessary to read in the word containing the desired byte. So the address of successive words differ by 1 word size, as you said. So this is the unique identity for this memory. And it is represented in hexadecimal numbers. Okay, so let's look at this. In the progress of this course, the address of a word is equal to what? Address of the first byte in word. So as you can see in this diagram, it's being packed, let's say, in chunks of each divisions of the memory system. So by conversion, ordering of bytes called endians, the two options are big endian and little endian, in which address does the least significant bytes based on Hilbert's travels. Tribes cast X on different sites. Okay, so scale 1, let's look at the big endian into bracket, that's the SPARC architecture design, and then its least significant byte and also has the highest address. Also, the little endian 86 times and the 86 by 64 bits also has the least significant byte and has the lowest address. Also, linking on with the endian, the bi-endian. So take note, we have the big endian, the little endian, the bi-endian, and this can be specified as big or little. And the least significant byte has highest addresses. And with this little endian, that's the 86 times the 86 by the 64 bits bytes has a lower address. And then endians only applies to memory storage, and it is determined memory storage order for multi-byte data. So let's look at addressing modes, several addressing modes of how these memories are addresses. We have what? The different ways of specifying the location of an operand in an instruction are called addressing modes. I hope you now know. So let's look at the implied addressing mode. In this addressing mode, the definition of the instruction itself specifies the operand implicitly. It is also called an implicit or inherent addressing mode. So you can jot that down. So for example, the instruction, that is the CMA, the complement accumulation, is an implied mode instruction. And in a stack organized computer, 0 addresses instructions are implied mode instructions, since the operand are always implied to present on the top of the stack. So So now let's look at this image. Okay. So, and then let's look at, before the image, let's look at operands. Is the object, is an object that is what? Operated by an operator. So since this object that is being operated by an operator are always implied and it's always presented on top of the stack on the memory system, so data is being directly stored in this address, as you can see the mouse cursor. And then as an example, the MOV. Okay, so let's look at other addressing modes. With this one, we have the immediate addressing mode, the direct addressing mode, the indirect addressing mode, the register indirect, the register direct addressing modes, the base register addressing modes. We have relative addressing mode, the index addressing mode, and then auto increment addressing mode. Since you have auto increment, we also have what? The auto decrement addressing mode. Okay. Let's look at the immediate addressing mode. In this addressing mode, the operand is specified in the what? Instruction explicitly. So we got to know in the implied addressing mode, the operand, the instruction itself is specified by the operand implicitly. And now in the immediate addressing mode, the instructions, the operand specify the instruction explicitly. Instead of address first, an operand field is present. So that operand field is present that contains the operand. So an example will be the what? The ADD 10 will increment the value stored in an accumulator by 10. We also have what? The direct addressing mode. And in this addressing mode, the address field of the instruction contains the effective address of the operand. So let's move forward since there are so many addressing modes. Okay, so now we look on to types of addresses. A memory address is a reference to a specific memory location that's used at various levels by a software and hardware. And then memory addresses are fixed lengths, sequence of digits, conventionally displayed and manipulated as unsigned integers. And then there are different types of memory addresses. So in our previous discussion, we got to know the several addressing modes. And now we are looking at types of memory addresses. Let's see. Okay. So let's continue. We have physical addresses, and these are the actual addresses of memory location in the computer's physical memory. They are used by the hardware to access memory directories. So this type of addresses, data is being what? Accessed by the memory directly. We also have the logical addresses, and these are the addresses used by the CPU, that is the central processing unit, to access memory. So there can be instances whereby data is being accessed from the memory directly, that is the physical address, and when the CPU is being used by the when the CPU and when the address is used by the CPU to access the memory, that is the logical address, and they are translated into physical addresses, that is what the MMU, the memory management unit. Moving on, we also have virtual addresses. These are the addresses used by a program when it accesses memory, and they are translated into logical addresses by the operating system. So with these virtual addresses, they are used by programs to access the data from the memory, and they are translated into logical addresses. So with these virtual addresses, it is this logical address. I see. It is this logical address. That's what translates them by the operating system. And then last of all, we also have what the pointer addresses, and these are addresses that hold the location of another memory address. And the pointer is a variable that stores a memory address. So take note. A pointer is a variable that stores a memory address. Okay, so as I bring today's lesson to an end, we got to know memory addressing, several addressing modes, and now with the types of memory addressing, we bring today's lesson to an end. Thank you for your time and attention.
Hello guys, so my name is Desmond Abisi Selassie. I'm in Group D, and I'm here to present on the flip-flop as a single bit storage cell. So why then is the flip-flop a single bit storage cell? It's so because it stores a single bit of data in two stable states, that is either one state is 0 or the other is 1. It can also be termed as a bistable vibrator, which means it has two stable states and it can remain in either state until a signal is applied to change its state. Yeah, so the flip-flop, so the basis of the flip-flop. So the flip-flop is a basic electronic circuit that serves as a single bit storage cell in digital circuit, and is used to store binary information, as you all know, is zeros and one. So it operates on a clock signal and has two stable states, as I talked about, the 0 and the 1. So the 0 can be reset and the 1 can be set, and it can be changed by applying varying inputs. Yeah. So the types of flip-flops. So mainly there are 4 types of flip-flops. The SR flip-flop, that's the set reset flip-flop, the JK flip-flop, the T flip-flop, and then the D flip-flop. So the difference in these flip-flops are the number of inputs they have and how they change states. So let's say SR can have 1 or 2 inputs, JK 5. So the number of inputs is what differentiates these types of flip-flops. So let's get right into SR flip-flop. So this is how the SR flip-flop looks like. So you can see it consists of these inputs, the S and the R, and outputs Q and Q prime, and these 2 inputs NAND gates, yeah, with the clock, yeah. And you can see it's cross coupled. The 2 NAND gates near the output, you can see it's cross multiplied as in an X, yeah. So that's it. That is also the truth table for the SR flip-flop, yeah. So when the S is 0 and R is 0, Q will be 0, and then the Q prime complements the Q, which gives us 1. So that's how the table is formed here. So let's describe the SR flip-flop. So this is the most basic sequential logic circuit consisting of a latch and has 2 inputs known as the set and the reset. So the S and the R, which stands for the reset and the reset. And so the SR flip-flop, this is the most basic sequential logic circuit consisting of a latch and has two inputs known as the set and the reset, as I talked about earlier. So the latch is the cross-coupled part of the flip-flop, the SR flip-flop, and the two inputs, as you can see, the S and the R, that is the set and then the reset. And it consists of two outputs, the Q and then the Q prime. Yeah. As you can see, the Q and then the Q prime, which are the inverse of each other. When Q is 0, Q prime will be 1. And the clock input used to trigger the flip-flop's operations. Changes in the inputs of S and R only take effect when the clock signal transitions from one stage to another. So with the CLK, you see that's the clock input. So it's used to trigger the operations of the S and R. It's what to determine if the S is 0 or 1 or if the R is 0 or 1. Yep. And then it's important to know that the SR flip-flop has limitations, including the potential issues with unstable or forbidden states. So when you look at the truth table, the last part, you see Q and then Q prime, it's infinity there. So that's the forbidden state of the SR flip-flop, its limitation. So with that part, Q and then Q prime will be the same. There will be no complement. That is why it's called the forbidden state, and it's its limitation. So with that problem, more advanced flip-flops like the D flip-flop and then the JK flip-flop have been developed to address these limitations and provide more predictable behavior. So there have been more of the flip-flop produced to eliminate that forbidden state that the SR flip-flop has. Yeah. So the next flip-flop I'll be talking about is the JK flip-flop. Yeah, so this is the JK flip-flop here, and it has two inputs, also like the SR flip-flop. So the J input and then the K input, and two outputs, the Q and then the Q prime. But you can see the output of Q prime is connected to the input of J, and then the output of Q is connected to the input of K. Yeah, so that's how the JK flip-flop is. So the JK flip-flop, named after Jack Kilby, he was a Texas engineer and he invented this flip-flop, and it's an improvised version of the SR flip-flop where the undefined state of the SR flip-flop is eliminated. So this was invented to solve the forbidden state of the SR flip-flop here, and it has two inputs like the other sequential circuits, and the set input of the JK flip-flop is known as J. So here the set input is known as J, and then the reset is known as the K. And then the JK flip-flop circuit can also be referred to as a gated SR flip-flop, which has an additional unit that is clock input. And there's an additional clock input because it prevents the invalid conditions which can occur during the set and then the reset input. So I'll use the truth table to explain this. So with the last part of the truth table, you can see the invalid states there, the dash dash. So with this JK flip-flop, the additional clock input is going to correct this by toggling between this output. So when it's 1 for Q, it will toggle it and make it 0, and when it's 0 for Q, it will toggle it and make it 1 for Q prime. So that's how it solves the forbidden state of the flip-flop. Yeah, so that's it. And so the next flip-flop, that's the T flip-flop. It's known as the toggle flip-flop because of its toggling operations, and it's a modified version of the JK flip-flop. And a T flip-flop is constructed by connecting the J and K inputs, creating a single input called T. Hence why a T flip-flop is also known as a single input JK flip-flop. So I use the logic diagram to explain So as you can see, the T flip-flop is the same as the JK flip-flop, but just some slight modifications to it. As you can see, the J and the K inputs are connected as one input. That is what the T. And then this is why it's termed as a single input JK flip-flop. Yeah. And then the clock signal must set high to toggle the output. So the clock signal must always be high to be able to change the outputs. That is the Q and then the Q prime. So it must always be high, that's one. So when it's low, there will be no change in the output of the flip-flop. And the T flip-flop only works when a clock signal is high. Yeah. So let's see the truth table. So when the T signal is set low, it will not affect the present state of the output and the response will not change. So as you can see, when the T signal is 0, nothing changes there, still 0 0, and then it's still 1 1. So when the T signal is set high, if the present output status is also 1, it converts it into low. So as you can see, when the T signal is 1, it converts. When the output is also 0, it converts it to 1, toggles it to 1, and then when it is 1, it toggles it to 0. It means the T signal is going to toggle the outputs right there. If it's 1, it will be 0. It's 0, it will be 1. Yeah. That's the T flip-flop. So in summary, these are the logic diagrams of the 4 main flip-flop. I'm not going to talk about the D flip-flop, so my colleague is going to talk more about the D flip-flop. Yeah, so this is the summary of all the 4 main flip-flops. Yeah. And finally, the uses of flip-flops. So flip-flops are used for making registers, as you can see, the shift and then the storage registers, and then the counters, which are used for increment and decrement in values. That's based on clock pulses. And then the memory units for temporal storing of data, and then synchronization, that's used to synchronize between different parts of a circuit. Yeah, so thank you. So my colleague here will continue on the rest of our presentation. Yeah, thank you.
Today we'll be having a short discussion about a type of flip-flop called D flip-flop, or simply called delay flip-flop. First of all, when we talk of a D flip-flop is a type of fundamental building blocks in digital logic circuit and computer architecture. Its main function is to store a single bit of information and synchronizing signals. It is featured or characterized by a clock input, a data input, and 2 other inputs. The 2 other inputs in question are the Q output and then the Q prime output. The Q prime output is the complement of the Q output. That means when clock signals transmissions data from one place to another, the data input is being transferred to the Q output. Now, this is a brief explanation about D flip-flop, or simply called delay flip-flop. Let's look at the truth table of D flip-flop, which will make this explanation or this thing quite easier. First of all, on our table we have the input and then the output. As I said earlier on, the output consists of the Q output and then the Q prime output. The Q prime output is the complement of the Q output. And also, whenever you see 0, that means it is in the off state. And whenever you see 1, 1 is in the on state. So you can all bear in mind that from the table, the data which is represented by the letter D and then the Q output, both of them are in the off state, meaning it is represented by 0 symbol. But the complement of the Q output will be the opposite of the 0, which is 1. And same applies to the second horizontal line or the second line, which is the 1. Both of them are in the on state, which is represented by 1. And the complement of the Q output will be 0. That is the truth table of the delay flip-flop or D flip-flop. Now, let's talk about the functions or advantages of D flip-flop. First of all, D flip-flop is used in registers. The registers, when I talk of the registers, I mean the one that is found in the central processing unit, or simply called CPU. It stores data temporarily during processing. For instance, registers can be used for arithmetic operations such as multiplication, addition, subtraction, division, among others. Second point for the use of D flip-flop is that it is used in memory elements. D flip-flops are used as memory cells in memory units, forming the basis of memory storage in central processing unit or CPU. And lastly, the third function or use of D flip-flop is that it is used in delay circuit in some cases. So guys, this is the brief history.
Hello guys, thank you for going through the presentation with us. During this presentation, we touched on various areas, and some of these areas are the memory system. We also touched on the memory addressing. We also touched on flip-flop as a single bit storage cell, and finally we touched on the D flip-flop. So when Percy was doing his presentation, he made us understand something under the memory system, that the memory system is a crucial component of modern computing devices responsible for storing and retrieving data. It is divided into two main types. We also learned that we have the primary memory and we have the secondary memory. And we got to know that the primary memory was also known as the RAM, which is the random access memory, which provides fast data access to the CPU and is volatile, meaning it loses its data when the power is turned off. And we also learned about the secondary memory, like the hard drives, the SSDs, that is the solid state drives, which is non-volatile and stores data even when power is off. We also came to understand that the memory system's efficiency depends on factors such as the access time, capacity, and the cost. Access time, capacity, and the cost. So this is a hierarchy of how the memory system and their allocations are. We have the CPU, we have the registers, we have the cache, and the cache have their various levels. Then it comes to the main memory, and under the main memory we can have the physical RAM, we can have the virtual RAM. Then we come to the secondary storage devices, which are not volatile, meaning they save data even when power is off. We have the ROM, we have the removable devices like the external hard drives and the pen drives. We have network, internet storage, we have hard drives. And then it comes to the I/O devices, that is the input output devices. And this is the hierarchy. Okay, so under Godfrey's presentation, we got to understand something under memory addressing. And we got to know that memory addressing simply refers to the method by which data is accessed in the memory system. And we also understood that the width of the memory address bus determines the maximum amount of memory that can be addressed. And we also got to understand that the memory addressing can be direct or indirect. And in the direct addressing, it involves using the actual memory address. But when we talk of the indirect addressing, it uses pointers to access data indirectly. Someone will be wondering what are these pointers. Pointers are simply data types that stores memory addresses in a variable form. They store memory addresses in a variable form. So simply when we are referring to pointers, what we are saying is that pointers are used to indirectly access the value stored in the memory location. They provide a way to work with the memory at a lower level, which can be useful for tasks like dynamic memory allocation, passing values by references. So here the CPU is not accessing the address directly, but rather is accessing it as it has been stored in a pointer. Okay, so we also, this is a diagram representation of actually how they regulate together to give us the results that we need. So here we have the CPU, we have the memory, and we have the I/O devices, and you can see that they are interrelated or interconnected by the control bus, the address bus, and the data bus. And simply what the control bus does is that the control bus is responsible for transmitting control signals between various components of the computer system. That is primarily between the CPU and other devices. So that is what the control bus does. And the address bus is used to transmit memory addresses between the CPU and the memory subsystems. So simply when the CPU wants to read or write from a specific memory location, it places the address of that location in the address bus, and the address bus specifically which memory location specifies which memory location or device the CPU intends to communicate with. Then it comes to the data bus. The data bus is responsible for carrying actual data between the CPU, memory, and other peripherals. So when the CPU reads or writes data to memory or peripherals, the data is transmitted over the data bus. So this is simply the diagram representation of what actually goes on when address are being requested for and data is being written on. And we also got to understand during Desmond's presentation on flip-flop as a single bit storage, we understood that flip-flops are basic building blocks of digital circuits serving as single bit storage cells. They are used to store binary data and are the foundation of sequential logic circuits. We also understood that flip-flop can be one or two states, that is, can be set to 1, that is on or high, and it can also be set to 0, that is off or low. The most common types of flip-flops are the SR flip-flops and the JK flip-flop and the D flip-flop. And he also elaborated more on that and made us understand how these flip-flops operate. And we also understood that these devices stores information and synchronize it with clock signals, allowing to control data storage and transfer. And we also understood that the stability of a flip-flop's output depends on its setup and hold times relative to the clock signals. So this is the simple and the NAND representation of the first one we have at our top left is the SR flip-flop, and the one we have at our top right is the JK flip-flop. I think my image has covered it, so let me bring it here so that you can see. That is the JK flip-flop. They have their input, they have the clock, then the output comes out. Then the last one at the bottom is the T flip-flop. The last one at the bottom is the T flip-flop. Okay, so Alan also came and elaborated us on the D flip-flop. He made us understood that the D flip-flop or the data or delay flip-flop is a fundamental digital circuit component that stores and outputs a single bit of data. It has a data input D, a clock input C, and outputs for both the stored data, which is the Q, and its complement, Q complement. So the D flip-flop state changes, that is data transfer, occurs on the rising or falling edge of the clock input depending on the specific design, because there are various designs for the D flip-flop. So the D flip-flop is widely used in digital systems for various applications including memory cells, data synchronization, and final state machines. So this is also a representation of the D flip-flop. It has its input, that is the D, it has a clock input, then it is being represented by the NAND and the OR operators, then it has its output Q and the complement Q. Thank you very much for joining us on this presentation. Any further questions on this presentation can be shared in the comment section and it will be addressed as soon as possible. Don't forget to like, share and subscribe for more content. Thank you all for joining us on this presentation. Thank you.